Hi, today we'll be discussing about sound. So, what exactly it is that sound, right, is a form of energy and it is generally produced through a vibration of a source. So, what we have in the human body, right, we actually have a vocal cord that actually will be able to release some form of air and what's, I mean, not say air lah, but what happens in the vocal cord, you have two flaps. These two flaps will actually vibrate, causing some vibration resulting in a production of sound, and that's how we actually talk. So in order to hear sound produced by this vibration must be transmitted from the source to our ear. So inside our ear, right, there's actually a simple eardrum that will actually be able to receive and detect these vibrations and send the signal into the brain to make sense of what these sounds are. So uh, in terms of the transmission of sound waves, right, we do recognize that you require a medium and that the transmission of this vibration is in a form of a sound wave. So when we talk about medium is in simple terms, we are looking at particles where the solid, liquid and gases are these particles are usually the medium to actually transmit the sound wave as they contain particles in them. In a vacuum, right, you do not have such particles, and because of the absence of these particles, sound wave cannot be traveled, and hence generally you won't be able to hear anything. So in the movie Gravity and what's not, right, you realize that even though there's an explosion at the back end, right, in the space shuttle, right, the astronauts by right cannot hear. Reason being because there is no form of particles in a vacuum of space to carry this vibration. So sound wave is an example of a longitudinal wave. In our previous few chapters, we learned that there are two types of wave. There's a transverse wave and a longitudinal wave. So in this case, sound, it is an example of a longitudinal wave. Now, what is the meaning of longitudinal wave, right? Is generally, right, what we can see, the vibration is in parallel with the motion of the particles. And in this case, right, what we can tell from this particular diagram is there is actually two main portion of longitudinal wave kind of behavior through particles drawing. Number one is this region, which is the compression. So in the area of compression, right, these particles are compressed tightly such that there is actually a large concentration of particles in this region as compared to the other one, which is the refraction. So in the refraction region, right, this is where there is a lower pressure of particles. Okay, so what happens is this movement will always move in a the particles will usually move in this kind of fashion. They'll move like this. They're left, right, back and forth, and each of it will actually hit one another. Okay, so that is generally how the whole behavior looks like. And then these back and forth movement of the particles will create regions of high pressure, which is the compression, and regions of low pressure, which is the refraction. Compression is, in this case, this high pressure region when all the air particles are pushed together, and then the opposite happens for refraction. Now, how are we then able to use this diagram, right, to translate into a wave diagram, right? So this is how it goes, where we could see that the peak let's say we draw a middle portion in all of the compression and refraction region. Okay, this is an aggregation. Okay, what we can see from here, right, this will actually help to indicate where the individual parts are. So when compression, right, compression happens, right, we are talking about the top part only. Whereas for the refraction, right, we are talking at the bottom part. So what we can see is once you have these two regions plotted, you could easily come out with the whole wave diagram. Do note that usually it can start around 0, 0 point of view, and then you can actually draw. So in this case, what we can see is how many waves are there, right, is decided by the number of let's see, let's say I use purple. Okay, so the number of wave is, so this constitute one wavelength. So from here, here, this is one wave. Okay, this is one wave. Agak-agak one wave. This would be the start of a second wave. You could see that they more or less constitute the same one, and this is somewhere of like a looks more of like a 3/4 of a wave. So it's 2 3/4 wavelength for this particular item here. Okay. So some of the questions that they can come up with is the formula of V equals F lambda, which is also from the previous chapter. Okay, do get this book. I think the GLM series for this is actually quite good in the form of like using for revision and things like this. Okay, next is experiment to show sound needs medium to transmit. So sounds will actually need a medium to transmit, and that the experiment investigates the requirement of medium in sound transmission. So when the electric supply is turned on, the bell ring can be heard. And when the vacuum pump is turned on, air is pumped up gradually. The bell ring is still working, but the sound faints gradually until no sound can be heard because the bell jar has become a vacuum. So when the air slowly returns to the bell jar, the sound of the bell ring can be heard again, and this experiment shows that sound requires a medium to transmit. It cannot transmit in a vacuum. So in other words, what am I trying to say is that initially there is a lot of gas particles found inside this bell jar, and therefore when you start the electrical bell, it will start to hit the bell, and you will be able to hear a ringing sound. Okay, that's because of the sound will travel through the gas particles inside the pump, the bell jar, and then it will hit onto the wall, the glass wall of the bell jar, and then later to the surrounding air outside of the bell jar into your ear. So that's how the whole vibration is being transmitted. What happens then is this yellow color region highlighted, which is the air inside the bell jar, gets removed through the vacuum pump, and now suddenly inside has no more air particles, so you create actually a vacuum condition. So even though the electrical bell is being hit, there is no medium that is able to take onto the vibration leading to the walls of the glass jar being hit, and hence a cascading effect such that you also cannot hear any form of sound. So this is the whole experiment to show that sound requires a medium in order to be transmitted. Now comes speed of sound. So when it comes to sound, right, we do recognize that sound travels through vibration. So in a sense, let's look at particles, right? Particles that are close to each other tends to be able to hit each other or collide with each other faster as compared to particles that are very far apart from each other. So in the form of in terms of speed, right, this vibration transfer is faster if the particles are close together. And now when we look at the three different states of matter, solid, liquid and gas, the particles are always very far apart as compared to solids that they are actually side by side or next to each other. So that is why for sound, right, it travels fastest in solid state. So any kind of substance that they give you, right, if it's in you first compare by state of matter, solid, liquid or gas, that will indicate to you the speed of sound. So in a solid state, the particles are able to vibrate and collide with each other faster as compared to, let's say, gas or air. Hence the speed of sound is a lot faster. Then some of you may ask, how come the speed of sound is 320 or 330 meters per second? That one is because we are talking with respect to air, the surrounding air around us. But when we are talking about, like, let's say in the water, let's say you swim and then you shout, right, the speed of sound is actually a lot faster, and then followed by metal. So metal is like, let's say you hit at the side, right, then you can hear. But to us, we can't tell the difference because all of them are very fast in the first place. So the speed of sound is generally faster in solid because the particles are very close to each other, and therefore they transfer the sound waves more efficiently. Now the reason why I put the 3 times 10 to the power 8 meter per second, this one is actually the speed of sound for, sorry, it's not a speed of sound, it's a speed of light. Okay, so okay, so how then, if let's say the question asks you to design an experiment to determine the speed of sound, how do you go about doing it? There's a few ways to go about doing it. One way is, for example, in this case, a direct method, where what can happen is, let's say a person opposite of you from, let's say, a very far, standing very far away from you, shoots an air pistol. Okay, and what you do is you hold onto the stopwatch, and then you time. So what you can do is, first of all, you determine the distance between the person and you, and when one of them fires, because you see when they fire, right, you will be able to see a flame at the mouth of the pistol. So, and speed of light is actually very fast. It's 8 times 10 to the power of 23. So what will happen is, through your eyes you can see the light first. Then what you do is you start to record. You start the stopwatch. Even though you may not hear a sound, but that's where you start the stopwatch, because at that point in time the sound has been released. So after, what you do is when you hear the sound, you stop the stopwatch. So the first start is when you see either a smoke or a flame. The second one you press to stop the stopwatch is when you hear the sound. So this difference in sound, right? The time taken for this difference, right, is actually the time for sound to actually travel to you. So that's one. So you know the distance because you actually measured the distance between you and the person who is shooting the air pistol. You have the sound, which is through your stopwatch. Then you apply the formula, distance equals to speed times time. Okay, this formula you learn it from the kinematics chapter. Then from that formula you can then calculate the speed of sound. So in this case, because the speed of sound is around in the air and what's not, generally that speed should come as close as 330 meter per second. Okay. Now next, we take a look at the characteristics of sound. So one very simple question is, they will ask you, based on the difference in pitch and frequency, how did sound actually change lah? So in terms of pitch, right, pitch is a way to for note is generally either very high or very low, and this is determined by the frequency of the sound wave. So what is meant by frequency? Comparing this graph, the one in purple, so if I will draw it out, it'll be something like that, versus this particular graph in red. Okay, what we can see is the red color wave, right, has actually more humps or more waves as compared to the one in purple. Hence, the one in red has higher frequency of sound. Being higher frequency of sound will generate a higher pitch to the sound. Whereas the one in purple, because it has lower frequency, you will have a lower pitch. Now, what is this pitch? Pitch is basically something like how high or how low your note is. For example, when you have a high pitch, you have a very squeaky, like a chipmunk kind of sound. Whereas a very low pitch is where you have a very deep and down voice. Like like let's say opera, they can do very, very low pitch kind of thing. So that is the main difference. So in exam, how they will ask is more towards of you assessing from a graph whether is there a high pitch or low pitch due to the frequency. You will definitely be asked to compare. You can't say from a particular graph and then you just interpret is it high or low. You have to do a comparison in terms of frequency. So that's the first one. Okay, and that for any human audible frequency range, right, is actually 20 hertz to 20,000 hertz. Sometimes in exam they may rewrite this as 20 kilohertz. Okay, so anything that isn't within this audio frequency, right, will not be you basically can't hear, but you can still see the vibration. So one very good example is, let's say in online YouTube videos, you could see that they put a radio beside or loud speaker beside a glass, and then some of this glass is still vibrating even though you can't hear the sound. It's because the frequency that they are using is actually higher or lower than the human audio range. For pets like dogs and what's not, they may have also different audio range. So sometimes like the dog whistle, you may not hear anything, but the dogs can hear because of the audio range. The second criteria is loudness. Loudness is determined heavily by the amplitude of the sound waves, meaning the height of the wave. So over here we can see that the one in the dotted line graph, right, has a higher amplitude height as compared to the solid wave, which has a lower one. Okay, so what can we tell? So the dotted line one, because it has a higher amplitude, it will result in a higher sound or louder sound, sorry. And then the one with the lower amplitude, lower in the form with respect to this axis, is the one that is softer. So what will happen, right, is when you look at this particular graph from the top, you see that because the height is the same, right, they have the same loudness and softness of the sound. Next, we look at reflection of sound. So sound, because it's a wave, it also follows some principles like light, whereby sound can actually be reflected from either a flat hard object. And since the reflection of sound obeys the law of reflection, there is this angle of incidence, and it has to be the same as the angle of reflection over here. Okay. So this is one thing to actually take note of. Next is we look at echo. What is then an echo? An echo is this reflected sound wave, right, that it bounces off either a hard or flat surface. So this generally comes out as a application calculation question. And one thing to note is that the distance, right, in this case is actually 2 times. Why? Because the distance traveled from the source, let's say the person is shouting, and then the person is able to hear echo. You could see that the sound travels twice. One time to reach the wall, and the second time bouncing off the wall back. So this is the total distance that the sound travel. Take note. So that takes place as compared to the earlier experiment where it's just one direction only. Okay, so the experiment to determine the distance using an echo can be set up as follows. So number one is you know the speed of sound. So this one is if let's say you are working on an environment like open air environment, we can assume that sound travels somewhere between 320 to 330 meters per second. Okay, next thing is the distance of the echo. Now, some of you may ask, when will we have this kind of situation? So imagine if let's say you are on a ship, you want to chart out the depth of the ocean. So that's where you will shoot some sound waves from the boat or the ship, such that when it hits onto the deepest end of the ocean bed and the sound gets bounced back up to the boat, you would see that will help you to actually map out the ocean bed's distance as well as a map of the ocean bed. Sometimes they also use it for fishing. So when they shoot down, it touches the fish, then it will bounce back up, right? So that at least you also know how deep to release the netting to catch the fish. So these are some examples. So in that sense, if you don't know the formula for echo for distance, right, then you have an issue already. You realize that you are lowering the net too low and not deep enough. Okay, so a receiver is used to detect the echo present, and so that's why you could see that the total distance is actually sound moving towards the wall and then reflecting back. So in this case, we could see that the total, still same formula, total distance equals speed times time, but if you are looking at finding the distance for just the speaker to the wall, okay, like let's say the question asks the depth of the ocean, then you have to remember to divide by 2 at the end. If they are asking you for a particular, just a one direction thing. So whenever questions, right, that is offered 2 marks, this is usually the kind of questions, and they ask for depth or distance from an echo. One of the mark is from dividing by 2. The other mark is actually calculated based on total distance equals to speed times time. Okay. So ultrasound, right, is a sound that has a frequency above the human hearing range, and it has a frequency above 20,000 hertz. So then some of these ultrasound has many different applications. For example, for the application of ultrasound, you can use quality control. So what is this quality control? It can be used to detect flaws or cracks in material. So let's say your underground piping, you have so many cement and what's not over it already. It is a bit hard to actually remove the whole piping just to check if there's crack and then put it back. So what happens is through ultrasound, by releasing ultrasound into the piping, right, and when it bounces off, we could actually tell to see which part of the piping is weak in signal. This will indicate that there is some form of cracks, because these cracks will lead to sound not reflected back but being able to penetrate through. So with this kind of location, we will then be able to detect which part of the piping that requires to be changed. The other one is prenatal scanning. So this one is for those pregnant lady, whereby they want to actually view if there is any kind of physical defect on the child or within the body. So sometimes when you have, like, let's say pain and you may feel some lumps in your body, right, one not so invasive mode will be the use of ultrasound to actually try to identify, to see if there is any form of unusual growth and things like this. Then of course through that, when they position the growth already, the doctor will then do a biopsy or what's not to actually detect the different tissues. The other one is locating objects underwater, which we just discussed just now. Echolocation, where they actually release sound waves down to map up or to determine the depth of the ocean. Sometimes it can also be used by fishermen to find the location of the fish through the signaling again. So that is all for sound. Other than that, I think we can proceed to our next chapter. Thank you.